Today we're going to start looking at projectile motion. This will probably take us a couple of days study. And projectile motion is when something is launched into the air. We ignore air resistance. Some of the problems may even take place on the moon where there is no air. But it's launched into the air and follows an arc through the sky and comes back to the ground or lands on something else. So that's what we'll be looking at. So we'll be interested in things that are launched. Maybe they land on top of a building or something like that. And so they'll travel a path something like this. Now, there is no acceleration in the horizontal direction. So in the horizontal direction, we can say that v sub x is going to equal v naught x. It stays the same the whole time. That means that x is going to equal x naught plus v naught x times t, and that's all there is to it. But in the vertical direction, and for these problems we'll always use up as the positive direction, we'll have the acceleration due to gravity. And so in that direction, just the velocity equation will look like v sub y is going to equal whatever it is at the start minus gt. That's something we've dealt with in our free fall problems before. And then we'll also have y is going to equal y naught plus v naught y t minus 1/2 gt squared. So that's what the y equation looks like. And these are things that we'll be using in just about all of the projectile motion problems that we do. Now, there's one other thing that happens, and usually or frequently we'll be given the initial velocity, but it'll be stated in some particular way. This is the velocity at the instant at which it leaves wherever it's launched from, and it'll be a vector, v naught, and we're usually given that it makes some angle with the horizontal, and we'll be given the magnitude of the vector, although sometimes we have to figure out the magnitude of the vector from how far away it ends up coming back to the ground. But in this case, if you play around with this, you find out that the horizontal component is going to be v naught, the magnitude of this vector, times the cosine of theta, and fiddle around with the trigonometry and convince yourself of this. And then the vertical component is going to be v naught sine of theta. And so v naught as a vector is going to equal v naught cosine theta in the I hat direction. And I just made an assumption here that the I hat direction is horizontal, and I'm going to have the j hat vector point straight up. So it'll be v naught cosine theta in the I hat direction plus v naught sine theta in the j hat direction. That's for something that's launched upward. Occasionally we may have something that's thrown downward off a cliff or something like that, and so the v naught vector may be pointing down in that direction. Well, we'd usually be given the angle at which it's thrown so that we'd know this angle theta. V naught x is still going to be v naught cosine of theta, but v naught y would be minus v naught sine theta in that case. And so that's something you'd have to take into account. When we combine all these things, we get the projectile motion equations that are on the formula sheet. And yeah, I think those will all show. Most of the projectile motion problems, you'd start by writing these down. All of these things, don't have to have them double spaced when you're writing them down, but that's the the way that you could combine them to start solving a problem. So let's give one a shot. For starters, I'll make up a fairly simple one. Here's the situation. A pool ball is shot horizontally off a flat table. It hits the floor 3.45 meters away. If the tabletop is 0.68 meters above the floor, what was the initial speed of the ball? Well, let's make a little sketch for this one. So here's the table that the pool ball was launched off of. Here's the floor down here, and the path of the pool ball in this case is going to be doing something like this. Okay, a little arc like that. The initial height above the floor is 0.68 meters, and the pool ball lands 3.45 meters away. Well, this is a projectile motion problem. And so I'm going to start by writing my projectile motion equations. I'll put them over here on the left side of the page, but I'll have v naught x is equal to v naught cosine of 0 in this case, which is just because it's launched horizontally, which is just going to be v naught. V naught y is 0. Okay. Usually it'd be v naught sine theta, but sine of 0 degrees is that. Then I'll have y equals y naught plus v naught y t minus 1/2 gt squared. In general, I would also have v sub y equals v naught y minus gt. These are the general forms of these equations, and so they're I haven't applied them to this problem yet. Like, for instance, v naught y is 0. But anyway, let's see. I've also got x equals x naught plus v naught x times t. And let's see, what else have I got? Oh, I'm going to write it sideways, which I don't usually like to do, but I'm out of paper. I will have, I think that'll still show, v sub x is going to equal v naught x, and it's constant. So that's what I have for these things. Now, I'm going to let x naught define it to be 0. That's just the starting point. But I'm going to let y naught equal 0.68 meters. So I'm choosing as my origin the point directly below here, directly below where the ball is launched from on the floor. And so y naught has that initial value. That's about as far as I can go for this thing. Writing the y equation though, with what I have, let's see, that v naught y is equal to 0, the y equation becomes, I'll go ahead and write the general form first, y naught plus v naught yt minus 1/2 gt squared will equal, in this case, it's going to be 0.68 meters minus 1/2 times 9.81 meters per second squared t squared. Okay, now when the ball strikes the floor, y is going to be 0. And so I'll have this 0 at some point in the future is going to equal 0.68 meters minus 1/2 times 9.81 meters per second squared times t squared. I'm back to using 9.81 meters per second squared again. I can't resist. Anyway, this is a simple equation. I can solve this thing for t. If I kick this term across, multiply both sides by 2 to get rid of that 1/2, and divide by 9.81 meters per second squared, that's 3 algebra steps at once. Do it slowly if you want. You could kick this term across first, have your 1/2 times 9.81 meters per second squared times t squared equals 0.68 meters, and then go on from there. But at any rate, I would end up, after 2 more algebra steps, with t equaling the square root of 2 times 0.68 meters divided by 9.81 meters per second squared. And I can solve for the time of flight. And I get 0.37 seconds. Now, unit-wise, inside there, I'll make a little aside here. I'm going to imagine on top I've got meters over 1, and I'm dividing by meters per second squared, which this thing flips and comes up here, and I'll have seconds squared per meter. And the meters go away, and I'll have seconds squared over 1, which is just seconds squared, and when you take the square root, you get seconds. So run through that in your head as often as you need to. That's the time of flight. Well, now I'm going to take my x equation, which is x equals x naught plus v naught x times t, or just v sub x times t, because they're the same thing, it's always the same. X naught is 0, and so I can take that out of that, and x will just equal v naught x times t, because x naught is 0. Now, when it hits the floor, 0.37 seconds will have passed, and it's 3.45 meters away. So 3.45 meters will equal v naught x times 0.37 seconds. And I'll be down to 2 significant figures for v naught x, but that's okay. I get about 9.3 meters per second. That was projectile motion. It was an interesting one. It was shot horizontally, but we figured out by measuring this distance how fast the pool ball was going. That'll be useful in a lab we're going to do in a few weeks. Let's try another one. This is one from the sheet you're working, or that you can print off if you want to. We have a projectile launched from the surface of the Earth with an initial velocity of 48.5 meters per second at an angle of 32.2 degrees with the surface. I'm going to make a little sketch of that. V naught as a vector, 48.5 meters per second. That's pretty quick. And it makes an angle of 32.2 degrees with the surface. Okay, well, if it's a projectile motion problem, I know I'm going to be using my projectile motion equations, so write them down real quick. V naught x equals v naught cos theta. I think I'll just figure it out while I'm at it here. V naught x is 41.0 meters per second. V naught y will equal v naught sine of theta. Plugging in the numbers, 48.5 meters per second times 32.2, you get 25.8 meters per second. That's for starters. Then my equations would look like this. Y equals y naught plus v naught yt minus 1/2 gt squared. X equals x naught plus v naught x times t. We can write the equation for v naught y, or v sub y. V sub y equals v naught y minus gt. It's launched from the surface of the Earth. Let's let x naught equals 0 and y naught equals 0. That's the launch point. We're free to do that anytime we want. And then it says, assume the projectile lands at the same elevation from which it was launched. All right, must be a flat plane or something like that. First question asks, what is the maximum height reached by the projectile? There are actually two ways to do this. I'm going to solve it by one of the methods where you would determine the time, then plug that into the y equation and figure out how high it happens to get. And then I'll show you what we can do with another equation that's a constant acceleration equation. Here's the thing, at the high point, the y velocity drops to 0. When it's traveling in this circular arc here, as long as it has y velocity, it's on the way up, but that y velocity is continually decreasing and it reaches 0 at the top, and then it starts coming back down. So the maximum height, you solve this. V sub y equals v naught y minus gt. Well, v sub y is 0 at the top, of the arc. So there's a little bit of explanation there. So v naught y will equal gt, t will equal v naught y over g. Now I could figure out that time, plug in the numbers, and then stick it into this equation, but I'm going to stick this expression into the equation instead, wherever there's a t. Remember now, y naught is equal to 0. So to find the high point, I'll just go y equals v naught y times v naught y over g minus 1/2 times g times v naught y over g squared. Whoops, that's v naught y. Okay, see what you can do when you're not afraid of algebra? Uh-oh. Well, let's try to simplify this a bit. Let's see. This first part would be v naught y over g minus the second part. When I square this, I'll have v naught y squared over g squared. I actually end up with v naught y squared over 2g. Okay, that's the maximum height. Well, let's see. I can get a common denominator with those two. Multiply top and bottom of this one by, whoops, this was v naught y squared, because it's v naught y times v naught y. Anyway, I'll end up with 2v naught y squared minus v naught y squared over 2g, which is what I'll have left is v naught y squared over 2g. That's the maximum height reached by the projectile. Let's find out what it is. V naught y, 25.8 meters per second squared, because it's v naught y squared, divided by 2 times 9.81 meters per second squared. And unit-wise, make a little side calculation. This isn't good form if you're actually solving a problem for turning in, but just check your units. On top you'll have meters squared per second squared. On the bottom you've got meters per second squared. When you invert this and multiply, you'll have seconds squared over meters. The seconds squared divide out. Meters squared over meters are just meters. Good. That's what we'd expect a length or height to be measured in. I get 33.9. So that's a pretty good height for that thing. How long is it in the air? How can we figure that out? Well, we look at our y equation. Y is equal to v naught y t minus 1/2 gt squared. And what's the value of y when it comes back to the ground? 0, right? That equals 0 when it hits the ground. And so I've got v naught yt minus 1/2 gt squared equals 0. That's a quadratic formula, except we can factor this, where after t, we can factor a t out of this, and we get t times v naught y minus 1/2 gt equals 0. And you remember from algebra, if you've got two things multiplied together equaling 0, then either this is 0 or this is 0, or maybe both. Well, one of the solutions I get here is that t is equal to 0. Well, that makes sense. That was when it was launched. Yes, the value of y was 0 at the launch. The other one will be v naught y minus 1/2 gt is equal to 0. Kick that over, multiply both sides by 2, divide by g, and you would get t is equal to 2 v naught y over g. Okay. This is leaving it in variable form until I get all the way to the end and then plugging in the numbers. Look at this, 2 v naught y over g. The time to the high point was v naught y over g. This one's twice as much. There's a symmetry to projectile motion that the object, if it lands at the same height from which it was launched, it will spend half of its time going up and half the time going down, and this will be the total time of flight. So that's pretty neat. Now, we can plug numbers into that, and we'll have 2 times 25.8 meters per second divided by 9.81 meters per second squared, and I get 5.26 seconds for the time of flight. How long is the projectile in the air? Now the last part, how far from the launch point does the projectile land? Well, it's traveling for this long. I've got an x equation that looks like this. This is c here. Just managed to get it onto the paper. Yes, it'll still show. Okay, well, x naught is 0, and v naught x is 41.0 meters per second. So I'll just have v naught xt, which is 41.0 meters per second times 5.26 seconds, which is 216 meters. Okay, there's our first projectile motion problem. We started by writing down the projectile motion equations, we actually calculated v naught x and v naught y while we were doing that, defined x naught and y naught to be 0, and then just proceeded to go through this problem. So that's the way we do these things. Before I stop this video, I want to revisit this top part. I'd said there were 2 ways to do it, and the way I just did it, I found this time that it takes to get to the top part, and I plug that into the y equation. I'll just redo that quickly. Y equals, let's see, I had said y naught was 0, so it's actually v naught y t minus 1/2 gt squared. And try to do it nicer this time. V naught y times v naught y over g minus 1/2 g times v naught y over g squared. I'm repeating this part, but that's okay. So that height will be y equals v naught y squared over g for the first term, minus, and I kind of quickly went through this thing. I'll do it a little slower this time. 1/2 g is actually g over 2, that's a g on top, not 9. Trying to make it more obvious. Times v naught y squared over g squared. And g over g squared will leave me a g on the bottom. So this ends up being v naught y squared over g minus v naught y squared over 2g. And I got a common denominator by multiplying top and bottom here by 2. And then my numerator becomes 2v naught y squared minus v naught y squared over 2g, which is v naught y squared over 2g. Okay, so that's what I got for the maximum height. There's another way to do that. What is the maximum height reached by the projectile? Well, here's an equation that we had. It says v squared minus v naught y squared equals minus 2g delta y. Okay, that's the one that came from v squared minus v naught squared equals 2a delta x. This one is the version you get when the acceleration is minus g, and we're talking about direction in the y thing. Well, the velocity at the top is 0, delta y, so I'll just have a minus v naught y squared equals minus 2g. Delta y is going to be y minus y naught, but y naught is 0. And so I get minus v naught y squared equals minus 2gy, minus on both sides. If I divide by or multiply by minus 1, it'll go away. Anyway, I'll end up with v naught y squared over 2g is equal to y. That's exactly what I had here. And so I could solve for the time, plug it into the thing and figure it out, or I could have used this equation to do that first part of the problem. And it's not uncommon that there will be two ways to do a problem.